Okay, so if we combine a couple of the equations that we now know, we have what we need to calculate the molar mass of a gas using an experiment, using experimental data. So those two equations are right in front of you. We've got this equation which tells us that moles can be calculated by dividing mass of a substance by its molar mass. If we rearrange that equation to get molar mass by itself, we should be reminded that molar mass is the grams of something per the moles, right? Molar mass is grams per mole. So in other words, if we can find something's mass and its moles and we divide them, we will have its molar mass. That's its grams per mole. Okay, now we have another equation here for gases. This is the ideal gas law. And we can rearrange this equation to solve for moles. So if I divide both sides by R over T, I'll end up with N moles of a gas can be calculated if we know its pressure and volume, the ideal gas constant, and its temperature. So PV over RT. So if I now combine these two equations, I'd get mass divided by PV over RT. So I replace N with the rest of that ideal gas law equation. And since I'm dividing by a fraction, it's easier to rearrange that equation as follows. And so if I want to get the molar mass of a gas, I can use this equation. And this equation is not in the data booklet, but you should be able to rearrange those other two equations. And the ideal gas law is in the data booklet. So knowing what molar mass is, knowing the ideal gas law, we can rearrange to have an equation that gives us the molar mass of a gas. So Mr. T over PV. It has a little rhyme to it, or you can just practice working it out. Okay, so if we think about that equation, then we can come down here to the experimental setup and think through what data would we need and how would we collect it. So usually when you collect a gas, you often collect it through water or over water. So you start off and you have an inverted container of some kind, usually a cylinder, and it's full of water. And then you're going to take your container of gas, connect it with a tube, and point the tube up into the cylinder so that as the gas is released, the gas will float up and it will displace the water. So eventually you'll have this space up at the top, which is where the gas is. So the gas is in here. Okay, so it's pretty easy to see that we'll be able to record the volume of gas if we use the cylinder. Now it is upside down. It does make it a little bit trickier, but we can get the V part, so the volume, we can get from the cylinder. So we're going to record the volume of the gas. So that's, if we look at our equation, we've got to record M, we've got to record T, we've got to record P and V. And ideally these should all be for the gas itself. Some of them we're going to have to make a few little assumptions on. So now we've figured out how to record the volume of the gas. We can collect the gas through water. That'll push the water out and we'll have our volume of gas collected in that cylinder. Okay, the mass of gas is also pretty straightforward. If we have this separate container over here, we just have to measure its change in mass. So number 2, to get the mass of gas, we just have to do the change in mass, so delta mass of the container. So mass before and mass after. And it should go down because the container is releasing the gas. So it's going to lose mass. Okay, these last two are a little bit trickier. They're a little bit more, not necessarily trickier, but we're going to make some assumptions. So number 3, temperature. Really what we want is the temperature of the gas. However, it's going to be tricky to actually measure the temperature of the gas directly because the gas is trapped up in this cylinder. So what we'll likely do is just measure the temperature of the room. And given enough time, the gas and the room should reach a sort of thermal equilibrium. And therefore, we can basically assume that they're more or less the same. So we're going to assume that the temperature of the room is the same as the temperature of the gas. Okay. Now, initially, as the gas is leaving the container, the gas is expanding. And so expanding gases tend to be cold. That has a cooling effect. And so initially the gas might actually be colder than the room. It also passes through the water, which may be a little bit colder than the room, depending on how long the water has been sitting out. So we just need to give it a little bit of time. And if we give it enough time, then the temperature of the room and the temperature of the gas should be more or less the same. Okay, the last thing is the pressure. We're definitely going to use a pressure probe or a barometer to measure the pressure of the room, which is the pressure of the air. Okay, so we're getting the pressure of the air out here. Now we have this concept that pressure tends to equalize. So the pressure of the air, as we've talked about, is pushing down on the surface of this liquid, and that's what's keeping the water and the gas up inside the cylinder. Now, technically, the pressure on the inside therefore has to equal the pressure of the air on the outside. But there's two things on the inside. There's the gas itself, which is what we care about, pressure of gas. But there's also some of the pressure is coming from this liquid water, this column of water that's still stuck in the cylinder as well. So technically the pressure of the air equals the pressure of our gas plus the pressure of whatever water is also in that cylinder above the surface level of the water. So one thing that we can do here is we can try to, if we have enough room in our container, in our trough, we can try to lower the cylinder down so that all that is above the water line is the gas. Okay, so that's what we're going to attempt to do when we do this in class. And if we get it that way, then the pressure of the gas inside the container is being balanced out by the pressure of the air outside the container. So we'll try to get rid of this part of the equation. If we don't quite manage to get it down there, then technically there's a way to figure out how much pressure that water is contributing. But for the most part, you're going to get to assume that the pressure of the gas inside the container is equal to the pressure outside the container. So we've got a couple of little assumptions here. Assumptions are always areas that if you were doing a lab report, these would be things to consider in your evaluation, whether or not those assumptions were valid and whether or not they had any influence on the results. But once we record all of these four values and we put them into the right units, we'll be able to calculate the molar mass of our gas. The mass should be in grams. The temperature needs to be in kelvins. And then pressure and volume usually go together as kPa and dm cubed. If we do that, we'll get our molar mass in grams per mole.